So, and warm welcome from my side after this official photograph. So, I will talk about aRTist, and it's not so much about art, but about RT, which is radiographic testing. So, it's about Industrial-Radiology, and this program will simulate the whole process. Yeah, my name is Carsten Bellon, and I come from the Federal Institute for Materials Testing and Research in Berlin. Also, the new affiliation of Christian. Yeah. So I will talk a little bit. What is the background? What the simulation is used for? Then I will explain the simulator and show some application scenarios. And I will end with a live demonstration. Yeah, radiographic testing. Probably not all of you are familiar with that. That is about weld testing, testing of constructions of bridges, and for instance of pipes. Here in a chemical plant, probably isolated pipes, but with radiography you can test it without removing the isolation, and it is about looking for corrosion and wall thickness measurement to look for the integrity of the installations. So that is all about non-destructive testing. That's the field we are working in. So we want to test the components without destroying them, so they should be in use afterwards. So another kind of non-destructive testing with X-rays is computed tomography. That's probably a little bit more familiar for everyone because it's used in medical area too. Yeah, here for instance a little turbine blade is mounted on a turntable. From the right there's a tube, and it will illuminate that digital detector, and after a full turn of the object you will get a reconstruction. And here for instance some floors are marked in red, cracks inside, so we are looking for internal structures, or for surface measurements where we then can measure wall thickness, or also for inner structures. Yeah. So why we want to model all these things? Yeah, non-destructive testing devices need to be accurate, so we need feasibility analysis, optimization of radiographic parameters, and for instance we have to train the personnel, and in all these fields simulation can help. For our simulator we had some objectives, for instance that we want to design the software for practitioners, so it should be easy to use and containing the relevant models to give real-world results. Yeah, how does radiography work? So we are talking about penetration radiography. So we have on one side the source. We will illuminate an object in front of a detector, and we get a shadow image. It's quite simple. So, and for simulation, the process is a chain. So we have a source model, we have an interaction model, and we have a detection. I will skip the geometry description. We will see in the program later on to speed up a little bit. So the first model is a physical model, is a X-ray generation, so we can define the tube parameters, where we have accelerated electrons hitting a target and producing Bremsstrahlung. Also, characteristic lines are counted from the target material, and of course, all the components have been evaluated to measurements. So here is a comparison between measurements and this spectrum simulations for two energies here, one in a 100 kV range and in a 200 kV range. The interaction is, there are several interaction mechanisms. Altogether, we are, for penetration radiography, we talk about attenuation. So X-rays going through the object and will be attenuated. There's a quite simple law. So there's an decrease with its length of the object, and we get a primary radiation image which gives the most information. But there are additional interaction mechanisms, for instance scattering and fluorescence inside the object that may disturb our nice shadow image. And to make a realistic simulation, we have to count for both contributions. And I told already the analytic description of the attenuation process is quite fast and simple, but for the general model for scattering isn't so easy. So there's one simple solution with some assumptions. You can use build-up factors, which is quite the same speed without additional effort in computing time. But if you want to consider general geometry, you need Monte Carlo models where you fire single photons and follow it through the objects. And to get an image, then you need a huge number. And so it needs much more computing time. So a little theory about the analytical model. So we only follow straight lines from the source to the detector. And here we have implemented optimized ray casting algorithm. So we only handle triangulated objects. So first we project all the triangles to the detector, and then we know which ray will hit which triangle, and so we avoid the heavy computations to figure out if the hitting or the interaction point between ray and triangle is inside or outside. Also, overlaying of objects is handled. I will go to that later on. And on the other way, the Monte Carlo model, just to depict that we follow single traces of a X-ray photon, and then by random number, the next interaction point is chosen, a next random number to find the interaction mechanism, next random number to find the new direction, the new energy, and so on. And so it will take a little to come to the detector then. Yeah, we have designed the aRTist simulator for simple handling of arbitrary geometries. We need interactive handling of all the parameters. You can select all the radiographic parameters, and integrated Monte Carlo model will also count for scatter radiation. All the interaction stuff and the GUI is done in Tickle. yeah, what were the reasons to choose Tickle? It's open source, platform independent. I think you know better than I. And then we integrated VTK, the visualization toolkit, to make all the 3D visualization, because it has also a bunch of additional function to process 3D and volumetric data, which we also use. Yeah, just a few features of VTK, if someone is not so familiar with that, but it's quite common toolkit for 3D applications, and it has yeah, an interpreted wrapper for several languages. In my case, we are using, or in our case, we're using TCL, and it has a compiled core, which we have extended for our ray tracer then to simulate radiographs. In the next, I want to show some application scenarios. For instance, here, assuming a casting part. Oh, that's not to be seen there. Just a pump casing, housing, and that's an STL with 90,000 triangles to have a good representation of the surface. Inside of the closed surface is a homogeneous material. Here we choose an aluminium. Then we set several radiographic parameters, and then a typical calculation here for an simulation for the analytical part takes just a few seconds, and for the Monte Carlo part, yeah, minutes probably, or mostly less than a minute. I don't want to bother you with the details, but let's better look for the results. Such primary image, so just the attenuated radiation coming straight to the detector gives such image, and in comparison, the scatter image on the right. And all the calculations here are done on a normal business PC. And of course, then we have built additional modules to automate some inspection procedures which are normal in our field. So, for instance, for computed tomography, you give with a few additional parameters the rotation of the object, and then the projections will be collected for different angles, and the reconstruction can be done also inside the simulator. For this configuration, I just want to attend that sometimes it's really needed to give this extended computing time for scatter generation, because if you look for the line profiles through the images, sometimes we have more scattered radiation than primary radiation, and that will influence the result of the computed tomography, for instance. If we now look for the reconstructed slice of this object, we see even without scatter contribution, we have some artifacts in the material. So normally that should be just one gray value because it's homogeneous material, but there are some extra lines here, a little bit dark if you draw your attention, or here in this case. And with scatter radiation, of course, that becomes more clear that there are influences by this extra radiation. Yeah. So here the simulation is a good tool to study these influences, because in reality, with your X-ray machine, you can't distinguish between scattered and direct radiation. But in simulation, only in simulation you have the chance to distinguish and to look for the differences in the image. Yeah, for instance, here, this is an image of a comparison of the virtual CT coordinates of the surface with the measured ones, so to study the influences, and then you can change parameters and look which parts of the image are more influenced than others. Probably I want to skip. I just want to emphasize that with the Monte Carlo simulation, we can follow single traces, and of course we can also visualize them then. So here is a special experiment for backscatter radiography, and we just visualize the first 40 photon traces hitting the detector. But this single photon traces to calculate takes a little bit longer. That's why we can calculate that remote on an HPC cluster if necessary. Yeah, and then I want to show you the software in work. Okay. Oops, what not? Sorry. Yeah, okay. Yeah, I will start aRTist. It shows up with like a normal Windows program, menu bar, toolbar, some tabs for the parameters, then the 3D area where we have the source position, some lines showing the borders of the radiation hitting the detector. And normally it's a little bit small, this screen. Yeah, then we have an image viewer showing the result. The result is also mapped into the scene. And let's start a first application. Let's look for a good object. We have some examples coming with the program. For instance, here, a surface scan of a real weldment takes a little to load it in, because we additionally compute an reduced representation for viewing it. And so we have here a weldment, some scratches here in the surface of this metal plate. We have here the assembly list with all the objects. There's the part with the material. And now, for instance, I can load in or generate another object. For instance, here a little sphere. That is now inside. Probably I should move the detector a little bit. I want to have it beneath. Yeah, there's also some mouse interaction here in the program. So if I change the material of the sphere to air, then we have here a little pore inside the weldment. Yeah, and of course, for a nice radiograph, there needs image quality indicators, and I just want to load one of it, and I have to bring it up to the surface. but that's my, yeah, ellipsoid. So I want to move this one, bring it up. I can change here the mode and can rotate it. So I want to have it lay over the image. And you probably have mentioned there's always a preview image, a live preview in the image viewer, but that the final image has to be calculated by clicking the run button and takes a few milliseconds longer here. We make some assumptions or simplifications to have always a live preview that you can handle all the objects quite smoothly and know what you are doing. And then comes some additional calculations. So I just want, oops, here is something wrong. No, wrong interaction mode. Yeah, I just want to show you this image because that looks quite nice, like in weld inspection. Yeah, to show a little bit more functionality, I load another project. So we generate, or you can save the whole work in one project file. And I have here prepared another one. Here we have a connection rod, and you should think about that this is mounted on a turntable. Then I probably first, I want to show, probably we need another object as a floor representation. Let's make a text, probably EuroTcl, maybe a little bit bigger. I hope this will fit. Oh, a little bit too much. Okay. I will let it like it is. It's now inside. Our object is from lead. I want to have it also that is from air, so it cuts out some material from our connection rod. And yeah, how to do an virtual computer tomography from it. We have several modules. Modules are extensions of the program which have their own GUI. And let's use CT scan. You have already seen there, see a dropping area where different modules can be dropped. You can also use them separately and drop it again. And the main factor is here to say how many projections you want to gather with a full turn. And I will start here the standard, which was the default value here. Only it's a very short example. So it will return the object and take 72 projections. We can follow here in the image viewer. And then an integrated reconstruction algorithm is started. The calculations are partially done on the graphics card, so that comes to fast results. And then I can show the result as volume rendering inside the scene. And for that I will switch off the objects we have used. And here we have then some volume rendering, and oh, I can't get the handle where it is. There it is. Yeah, I want to make it a little bit smoother. So then it should give a good representation of our object. If we look further into, yeah, we see some holes from our letters, EuroTcl letters. Yeah. With TCL, we have all the possibilities to open TK console, to give commands by scripting. So, and we also implemented with help of the TK-con the possibility to remote control by open a TCP socket, so I can control it from other programs. Yeah, we use the themed widgets here. Probably some extensions. You can click on the frames here to fold them, to give some space. In some occasions, it's quite useful. Yeah,
Which widgets? I don't get a name.
TTK. It's TTK.
Ah, okay.
Yeah, yeah.
This collapsing of groups is standard feature of TTK.
No, but doesn't push out the.
You added some bindings.
Yeah, yeah, yeah. And yeah, there are a bunch of settings, so we can use the icon style and icons. Yeah, for instance, here we have not the place to display all the icons. I could go to a small GUI style and restart the program. Then, yeah, okay, we will lose our results, but then we will see all the icons available. Yeah, and due to the possibilities in VTK, we, for instance, also have stereo rendering with colored glasses if you want to attract some users. Yeah. So I think with that I gave an impression how the program runs, and probably there are some questions about how that is implemented or works. Yeah. Thank you.
Do you integrate the VTK in the package when you deploy it?
Yes. Yes.
How large is the whole package?
The whole package is about 100 megabyte, including TCL with all the packages and VTK and all the extra program. We have some command line programs we call from inside TCL.
Probably the VTK occupies the most.
Yes, it will. Yeah, yeah. So there are 20 or 25 DLLs, which we have to. Yeah.
No further questions? Then again, Carsten, thank you for a very interesting talk. We will do it the same procedure as yesterday. Christian, I think you should take your list with the numbers. So before